Okay, class, this is 7B problem set. So we're just about finished with chapter 7. So let's take a look at electron configurations with ions. Notice that manganese is in the transition metals. So here's something you should all know, that when we write electron configurations with ions and the metal is in the transition metals, there we go. You know what? Gotta love technology. There we go. In the transition metals, the S sublevel, sublevel S is taken first. Okay, now what does that mean exactly? Well, let me write out the ground state or without. So if I'm just talking about manganese, manganese is number 25. Number 25 is I'm going to do the abbreviated, short, condensed, like whatever you want to call it. That would be argon, like this. It would be 4s2, 3d5. Okay? That's without the charge, just manganese. So when we take electrons to make a charge of a +3, I'm going to take the S goes first. Okay, so for all of these, the S goes first if your metal is in the transition metals, not the D. Typically we take it from the last term, and that would be 3d5, but we take 2 from here and we take 1 from there. So that changes, like, ooh, I didn't write that correctly. That would be a 4 here and a 1 from there, and when I add these two together I get 3 electrons, which is how I get rid of the 3 electrons to get a +3 from this. So if I rewrite this now, I have manganese +3 is still going to be argon, and all I'm left with then is a 3d4, like that. Okay, so the big, like, new concept is transition metals. Always we take the sublevel S first. There's going to be 2. There's going to be an S and a D, and we take the S first. Now selenium is not a transition metal, so let's write down what we got here first. I'm just going to do, you don't have to do this for your answers when you write this down, but I'm going to show you what selenium looks like without the charge. So that's going to be, selenium is in the 4th group, so it's still going to be the 4th period, so it's still argon, like this, and it's going to be 4s2, 3d10, and then 4p4, like that. Notice that 4p4 means that you can have another 2 electrons in here. Oh, by the way, for letter A, it says determine which have noble gas configurations. This is not a noble, not noble gas. Okay, not noble gas for argon 3d4. That is not a noble gas configuration. So if I add 2 electrons, because if I have a -2, that means I'm adding 2 electrons. I'm going back to selenium now. So when I do my selenium with a -2 charge, it's still going to be argon, like this, and that's going to be 4s2, 3d10, and then clearly my 4p is where I'm going to add the 2 electrons that it's gaining. So that's going to be a 4p6. And of course that is a noble gas configuration. So noble gas, like that. So the last 2 electrons are added here to make this 4p6, which is why selenium gets a -2 and not a -3 or a -1. So how about scandium? Okay, so scandium is a transition metal. Let's see what happens. So I'm going to write down scandium without the charge and see what happens. This is again argon, 4s2, 3d1. Okay, that is net charge of 0, so that's the atom. So scandium with a +3 means I'm ripping away 3 electrons. Well, isn't that nice, because I have 2 and a 1 here, which means I'm going to end up with argon, and that's it. Okay, so argon and nothing after that, because I've taken off the only 3 electrons that are outside of argon, which means that this is a noble gas configuration. I'm going to let you do the last 3 for letters D, E, and F. It looks like they are all transition metals. Thallium is not transition. Thallium is the first one in the P, and we treat that one just like if we're taking a P or an S, we take those right out of the P. And there's only, that's a +1, okay? But both Ru, let me check to see where Ru is. Ru is number 44 and gold is number 79, and they're both transition metals, so take the S's first when you do this. Okay, moving on to the next. So 64, write the balanced equation for the following reactions. This is all stuff that's contained within, obviously, the problems, the chapter sections. So let's take a look at these. I'm going to do the first two, and then you can do the last two. Potassium oxide. So now you have to write this stuff out. Potassium oxide, potassium has a +1, oxygen has a -2. We haven't done this stuff in a long time. With water, so that's H2O like that. So when I crisscross here, I get K2O like that, and I get rid of the charges. Okay, so now this says that, I'd have to check to see what page it is, but this is probably 7.7 when they talk about alkali metals. So whatever the pages are for section 7.7, when they talk about how alkali metals and oxides react with, I said it's probably, I'm not sure exactly where it is, but it's somewhere in there, second half of the chapter. So whenever an alkali oxide mixes with water, we end up with just KOH, like that. I have two potassiums here, so that means that I have two potassiums on this side. And notice that if I put one more oxygen with the H2O, that means I have two hydrogens and two oxygens, which is what I have here when I put the 2 in front. That's why I put the 2 in front. So we got to write the balanced equations. So diphosphorus trioxide. Okay, this one here is a molecular compound, which means we're using the prefix method. So P2O3, di means 2 and tri means 3, plus water, like this. Okay, so what happens on the other side here? Well, when I add them up, I have 2 hydrogens, I have 2 phosphorus. Uh-oh. I think I'm wrong with this. I'm going to have to do some balancing here. So when I change hydrogen, phosphorus, and oxygen, I'm going to combine them all into a synthesis reaction. You should look, I'm not sure if this is 7.8 with the non-metals. I don't think it is. I think this is an oxygen thing, so I think this is the second half of 7.7. Maybe it's 7.8. Honestly, I'm not really sure, but you should be able to find an example of this in the book. And when we have non-metal plus water, we end up with an acid. Now, all phosphorus compounds, the H3PO4 is phosphoric acid, H3PO3 is phosphorus acid. So this is going to end up being, I believe, phosphorus acid, which means H3PO3, like that. Let's see if we can get this to balance. So here I have 3 hydrogens, and here I have 2, which means I need to put a 3 in front and a 2 in front like this, and that will give me 6 hydrogens on both sides. Now that gives me 3 oxygens here, plus another 3 oxygens there, gives me a total of 6. 2 times 3 gives me 6 oxygens there, and then 2 times 1 for PO3, for the 1 for the P, gives me 2, and I have 2 there. So that actually balances with a 1, a 3, and a 2. All right, I'm going to let you check out C and D. If you want to, if you want to get full credit for this, then I want you guys to work on C and D and answer those in the problem set. Okay, let's keep going. 68, and then we'll answer 68, and then we'll cut this off and do, and I'll do a part 2 then, because there's also some stuff. There's 76 and some stuff for the test. Why is cesium more reactive towards water than lithium? Well, that's pretty easy to say. Cesium is larger, which means that the electron, that extra valence electron, comes off easier. What I'm talking about that's supposed to say easier. There we go. What I'm talking about, of course, is the ionization energy is lower for cesium than it is for lithium. So lithium, I should say it like this, it would be less than. So the mouth of the alligator opens to the bigger quantity. Okay, so cesium's larger, which means the electron is further away from the nucleus, which means it's easier to pull off, which means the ionization energy is less. Okay, let's talk about one of the alkali metals reacts with oxygen to form a solid white substance. So that solid white substance is dissolved in water. The solution gives a positive test for hydrogen peroxide. Okay, so if you have, first of all, it says in the burner flame, a lilac purple flame is produced. That is clearly potassium. Potassium with oxygen can react to form a peroxide. If I put peroxide and water together, what I end up with then typically is potassium oxide like this and hydrogen peroxide. Okay, so that is something that's definitely happening. So what is the white substance? The white substance is potassium hydroxide, and then once it mixes with water, I get potassium oxide and H2O2. So what's the identity of the metal? Clearly, with the whole thing that gave it away was the lilac purple. That would be potassium. If it would be red, it would be lithium. If it would be yellow, it would be sodium. Okay, so what's the identity of the metal is potassium. Now this says write the balanced chemical equation for the reaction of the white substance with water. Oh, we just did that. So I just answered that on the previous slide right here at the bottom. So potassium peroxide plus water gives us potassium oxide plus hydrogen peroxide. I didn't balance that. Let's see if we need to balance this at all. I got 2 plus 1 is 3. I got 1 plus 2 is 2. So now it looks like we're all balanced. Okay, nice work.